Hello, everyone. My name is Jiajian, and I'm glad to present our recent work WIC, which introduces a novel GPU communication framework with a warp-level interrupt mechanism to hide the synchronization overhead behind computations. So let's talk about the GPU communication. First, we define what we mean by inter-device communication. This doesn't just mean GPU to GPU or inter-GPU communication. It also includes communication between the GPU and the host CPU. Okay, as we move to more complex and large-scale parallel computing tasks, inter-device communication becomes absolutely critical. Sure, we've made great progress in fabrics and architectures like GPU direct P2P, peer-to-peer, and RDMA, and fast interconnects like NVLinks. But even with all these advancements, one issue continues to stand out: synchronization. And this isn't just about having fast links. It's about coordinating when data is ready and when it can be used. Currently, most of this coordination is left to the program. Typically, the consumer checks again and again whether the producer has made the data available. This kind of repetitive polling can seriously drag down performance and add complexity to system design. So while we've improved bandwidth, we still face a big challenge: synchronization or the timing of data transfer. Okay, now most current research is trying to hide the synchronization delays behind computation. Traditionally, this has been done by scheduling kernels. We run other computation kernels, K0, K1, and to Kn with data transfer kernels so that synchronization overhead is masked by other computations, which improves the throughput. But here's the catch. Even with the clever scheduling, the actual compute time of producer consume here and consumer kernels here isn't reduced. So to go deeper, more fine-grained optimizations have been exploited with kernels themselves. This called in-kernel. So these in-kernel strategies allow asynchronous data transfer without stopping the kernel execution. A lot of these works focus on the producer side, including scheduling additional transfer threads or employing page placement to dispatch data earlier. And on the consumer side, there's an interesting solution called GPS, which basically assumes that producer data will be ready ahead of time and push it to the consumer proactively. But in our experiments, we saw a different story. The real synchronization bottleneck actually shows up on the consumer side, not the producer, which is where most of the current research is concentrated on. And in most cases, things don't quite work like GPU assumes the producer data usually isn't ready before the consumers ask for it. So that proactive strategy doesn't always help. But before diving into our findings, we first took a step back and looked at how GPU communication behavior is analyzed. And we proposed a new analyze methodology. Most GPU communication research relies on traditional memory access patterns to select benchmark, but this can be misleading. These patterns generally provide a global view of memory behavior rather than reflecting the specific dynamics of device interaction. For example, the biotonics sort algorithm. This algorithm uses a random memory access pattern. However, its inter-device communication essentially for the global merging phase mainly shows a gather-scatter pattern. So we proposed a new angle on access pattern in GPU communications, like streaming, adjacent, scatter-gather, and random. And we also proposed another dimensional classification based on communication models, which describe how data is transferred across a synchronized routes. Okay. And additionally, to validate this framework, we selected 10 applications from 6 benchmark suites, ensuring they covered diverse communication patterns. We also included the CH3D, a communication-intensive case. This approach helps us avoid benchmarking crimes. Okay, and now building on our analysis methodology, here's what we found. We first established that consumer side overhead is the biggest performance bottleneck. We then identified that repetitive polling is the main source of this overhead. And then we dug deeper into the thread level behavior. We noticed something interesting. Polling often starts too early, before the producer has actually made the data available. This early polling doesn't help, In fact, it makes things worse. It creates resources contention. Okay, so let's take a closer look at the underlying reasons. In traditional single-thread CPU, you can imagine it. In the producer-consumer models, polling usually begins after all computation has finished. So whether you are polling or waiting by interrupts doesn't change much. There's simply nothing left to compute, but things are very different on GPUs. Consumer kernels don't run as a single thread. They execute as thousands of threads in parallel, often organized into warps. And these threads don't all finish at the same time. Some threads might completely quickly, while others lag behind due to some reasons like computational variabilities or memory stores. And here's what we found. Polling often starts too early, before many threads have finished their own work. And as you can see in this figure, threads E0 and to E2 are still active, while others have already started polling. This means polling doesn't just sit there waiting. It actually competes for resources with ongoing useful tasks. That's a big waste. And we can see even worse, after polling ends, some threads like E3 and E4 are still not done. That means that the synchronization phase could have been hidden behind those tasks. Okay, so this brings us our solution or the main idea. So WIC, warp level interrupt-based communication. WIC flips the model. Instead of letting polling dominate the warp schedule, WIC tracks polling frequency at the warp level. When it detects that a warp is spinning too early, it preempts it and stalling the warp and allowing other unfinished computations like E3 and E4 to run first. Once the data from the producer is finally ready, WIC resumes the stalled warp. In short, we turn synchronization from a blocking behavior into a background one, hiding synchronization behind the computation. Okay, so WIC is built around three key components. First, we have the interrupts. Its job is to detect when a warp is about to start polling for produced data. Instead of letting it just sit there and spin, the interrupt stores it and swaps in other executable warps that just have useful work to do. Next comes to the monitor. This module is constantly watching for the arrival of the producer data. It knows when the data becomes available and keeps the system informed. Then we have the activator. Once the producer's data is ready, the activator brings back the warp that was previously stored, just in time to consume the data without wasting cycles on repeated checks. Okay, so and to make all of this actual work on real system, WIC is implanted within the UVM framework. We use UVM page placement not only to transfer communication data, but also to check whether the producer data is ready. All changes happen inside, happen in the UVM context, or we say inside the UVM host kernel, which means programmers don't have to change a single line of code. And users just issue a data request like making a system call, and WIC handles the rest. It's fully transparent from the program's point of view. Okay. So how WIC works end to end? The whole process start on the consumer side, where our warp needs data from the producer. So instead of immediately polling, it sends a request to the interrupt, and then the interrupter allocates a free page in the UVM on the host, depending on how much data is needed. Then it redirects the warp to access that page, which triggers a page fault. And that's how we store the warp deliberately, rather than letting it busy waiting or waste GPU cycles. And then the balls move to the host UVM kernel. The monitor module catches that special page fault and checking if the producer data is available. If not, we just suspends the fault and puts it in a queue, waiting until the data is ready. Meanwhile, the monitor is constantly watching for which producer data is available. Once the data becomes available, all the now ready faults are passed to the activator module. The activator writes the producer data directly into the fault page and sends a replay signal to bring the stored consumer warp back to life. And finally, after the data is consumed, the page are released and recycled for future use. This whole mechanism let us completely hide the synchronization latency behind the ongoing computations. No polling and no ideal GPU warps. Okay, so now let's take a look at how WIC actually performs. We start by evaluating the overall performance compared to traditional cross-device communication methods. Then we go, go a step further and examine why WIC helps. Specifically, does it really allow more executable tasks to run while synchronization is still ongoing? That's something we raised earlier in the motivation section. And here we put it to the test. And we also analyzed the overhead introduced by WIC. And finally, we test WIC's scalability. And of course, we also compared it with existing SOTA system to see where WIC stands. Okay, so first, overall performance. We compare overall performance against traditional cross-device communication from two angles. The performance gains its brain and how it changed the breakdown of communication overhead. From the results, we've got three clear takeaways. First, WIC gives a big improvement to communication efficiency overall. Second, it works well across different communication scenarios. And third, it cuts down consumer-side communication overhead quite a lot. Okay, and the motivation. Okay, the motivation is demonstrating. Remember, in our motivation, we pinpoint that earlier polling with computation. Here, we evaluate whether we could really let more useful tasks finish before synchronization kicks in. The results show that with WIC, most of work gets done before waking starts. And more importantly, a large part of synchronization delay is now effective hidden behind ongoing computation, which is exactly what we wanted. Better communication efficiency without wasting GPU resources. Okay, and then we test how WIC performs as well as the overhead. First, the scaling. We scale up the number of threads from just 64 to 1 million. The results show that WIC keeps delivering consistent performance gains even at large thread scales. As for overhead, we looked at both the consumer side and the host side. Overall, the overhead introduced by WIC is quite small, and more importantly, it stays stable across different applications. And finally, we compare WIC with several SOTA systems from both CPU and GPU and the inter-GPU communication research. And across a wide range of applications, WIC consistently outperforms most of these SOTA methods. Okay, so that wraps up my talk today, and thank you so much for your time and attention. I also wanted to take a moment to sincerely thank our shepherd, Dr. Panda, and the anonymous reviewers for their insightful and constructive comments. And if you have some questions or thoughts, feel free to reach out. My contact info is right here. Thanks.